While there certainly is a lot of art to making polyurethanes, there definitely is a lot of science to it as well. And I'm here to teach you the science part of it. The magic part, I think you'll have to learn along the way. So the training topics for today, I'm going to start out with, talking about the chemistry for the flexible foams. So many of what I'm talking about today can apply to other types of polyurethanes, but it may not. And when there's differences between the flexible area and some of the other areas like rigids or elastomers, I'll try to point them out. I'm going to start out with, just a brief overview of the chemistry of foams, and then talk about all the different raw materials that go into making a polyurethane foam. And so it's a lot of material to cover. We're going to be trying to move fairly quickly, but there will be time for questions either at the end or at the intermission, and I'm here for the whole conference. So start out with what is a polyurethane. So by definition, a urethane is a chemical that has this structure here, NH, carbonyl oxygen. It's also called a carbonate structure. The most practical commercial route to forming that structure is by the reaction of an isocyanate with an alcohol. Polyurethanes, you see, have been invented about 80 years ago by Otto Bayer. So they've been around for quite a long time, but there's always continued new development in the technology. To make the polymer, you need a multifunctional isocyanate and a multifunctional alcohol, which is called a polyol. So shown here is a reaction of TDI with a diol would give you this linear type polyurethane structure. So there's two basic reactions in polyurethane foam chemistry. That reaction that I just talked about, the isocyanate reacting with the polyol to form the urethane, is called the gel reaction. What it's doing is this is building the molecular weight and is creating what we call the soft segments, which I'll explain further in a minute. There's also another reaction called the blow reaction that generates the carbon dioxide gas to turn that polymer into a foam material. So the blow reaction is react isocyanate with water. It forms this unstable carbamic acid intermediate that loses carbon dioxide to form the amine. Well, isocyanates are very reactive material, will react with anything with an active hydrogen, so that amine that's generated will react with additional isocyanate to form a urea. So this is called the blow reaction because it liberates the carbon dioxide to cause the foaming, and this creates what's called the hard segments of the polymer. Both of these reactions involve a significant amount of heat that we'll talk about later as well. And foam formation requires really a balance between these two reactions, that you have to balance the rate at which the blow reaction and the gel reaction occurs. The blow reaction typically predominates in the early stages, the gel later on as the foam is rising, and through choice of the polyols and the catalysis is how you control that reactivity balance. Isocyanates will also undergo a number of side reactions. As I indicated, they can react with anything with an active hydrogen, so that urethane structure has an active hydrogen as well as the ureas have active hydrogens. So if isocyanate reacts with the urethane, it forms what's called an olefenate. With the urea, it's called a biuret. And typically, these happen more when there's excess isocyanate there. And notice that these reactions are reversible under the heat. There are a number of other urethane reactions that the isocyanates undergo. Most of these are really not applicable to polyurethane flexible foam, more for some of the other foam or elastomer technologies and coatings, but just wanted to make you aware of them. So if you think about polyurethanes as a network, for the flexible foam, it's a thermoset as opposed to a thermoplastic type polymer, and you have alternating linkages of where the isocyanate was to form the hard segments and the long, flexible polyol chains. This is really not drawn to scale here. But the most common isocyanate for flexible foams is TDI, so it's a difunctional material. The most common polyol is a glycerin-initiated. So you can see that most of the linkages for that polymer network are created through the polyol side rather than the isocyanate side. Again, thinking of that isocyanate polyol water reaction, you're forming a urethane urea block copolymer, where you have that polyol, which is that soft, flexible segment, and then the hard segment that's coming from the urea water reaction. So the soft segment, what it does is it imparts that elasticity, the flexibility, and the resiliency to the foam. The hard segment, you can see how because of all you can get a lot of hydrogen bonding, that those hard segments kind of align together, and those hard segments impart that rigidity, the hardness, and the flex modulus, as well as the high temperature property for the polymer. So I think most people say they probably know what a foam is, but here's the definition that you have air or gas bubbles are trapped inside a solid or liquid. For flexible foam, it's obviously the solid, but it starts off as a liquid. And what happens as you go from that liquid phase to becoming a solid is important, and we'll talk about that later on. But the two main types of cellular foam are either an open-celled foam or a closed-cell foam. Closed-cell foam is more the rigid type foam. The flexible foams are the open-type cells. So when we'll talk about the mechanism later on for the cell formation, but when those bubbles pop, those cell windows will drain into form what's called the struts or the cell walls. In some type of foams, they open, by themselves. And with certain foams like the high resiliency or molded foams, they have to be mechanically crushed to give them that open cell, structure or nature to it. But having that open like that, what gives it the flexibility and high airflow. So besides whether the foam was open or closed, the other variables are things like what is the cell structure like, whether it's a fairly regular cell, as it typically is for conventional and viscoelastic foam, or high resiliency foams typically have a very irregular cell structure. The other variable here is often people count how many cells per inch there are. So, by the fineness of the cells will also affect foam properties. There's another type of foam out there called reticulated foam. It's typically made from a conventional foam through either chemical or mechanical degradation to produce the very large cells, and that's used for applications like filters or maybe outdoor furniture where you need very super high airflow or water to easily drain from that. So flexible foams can be classified in a number of different ways. The first is primarily the process that it's made, whether it's made by a slab stock or a molded technique. It can be classified by some performance property. Typically, the two main performance characteristics are density and IFD, which is indentation force deflection, how much force it takes to compress the foam. Three main classes of foams that we'll talk about are conventional foam, high resiliency, HR, or viscoelastic or memory foams. Some people also can classify foams by the end use application as well. You'll learn more about the specifics of the foam process in the later sections, but just basically point out that most flexible foam is made by a continuous process where the polyol and all the ingredients are kneaded separately to a mix head, along with the isocyanate separate into some type of laydown continuous pour process. You can see you can produce pretty large size buns. Flexible foam is made this way as opposed to most other type of foams because of the large volumes and everything, and a lot of other systems area all these components are often pre-blended. So that's a distinction of slab stock foam production. You can also, essentially, if you're making flexible foam in the lab, you're mixing all the components together in a small container and then just dumping it into a small box or open bucket and allow it to free rise. A larger version of that is called the box foam production. Essentially, it's more of a batch process. That's still practiced today, mainly by either very small companies or mainly in developing nations. So you still can produce foam that way. Molded foam, as the name implies, it's poured into a mold, and again, you'll hear more about that in the later sections, but that's how, like a molded seat or a molded pillow is made. Talk about flexible foam grades. They said the two main characteristics are density. Flexible foam can go anywhere down from about a half a pound or a pound per cubic foot up to about 8 pounds per cubic foot for some viscoelastic foam. Generally, the higher the density, the better the quality of that foam. The other variable was the firmness, which is the indentation force deflection, how much force it takes to compress that 25%. So you can go from sort of very, very soft from only 5 pounds up to a very, very super firm foam that might be used for like a packaging type application. And a very common technique a lot of people use when they refer to the grade of the foam is they'll use the first two digits refer to the density and the second two refer to the firmness. So 1015 means a 1 pound foam, 15 IFD, or you could have a 1 pound foam with a 30 IFD, or keep the IFD constant and have a 2530, just a higher density foam. That's a common technique a lot of people use, as well as again, other techniques, refer more to the end application of the foam. What I want to do is try to explain a little bit of the differences between conventional and a high resiliency and then a memory foam. So an HR foam, high resiliency, as the name implies, has the very high resiliency, greater than 55% compared to conventional foam, which is a lower resiliency. But also more important, and why it's good for seating application, is what's called the sag factor. And what these curves over here, these charts, it's plotting indentation force deflection versus compression. How much force it requires to compress the foam to a certain degree. So in a conventional foam, you can see there's a very steep initial curve here. And so what that means is it takes a lot of force to compress the foam a little bit. And then you have that flat plateau here where very little change in force has a big effect on how much foam that compresses. As a result, that a person or somebody with a very little weight doesn't have enough force to compress it, is sitting on top of the foam. Something with higher weight really compresses it, and the foam is said to bottom out. Whereas if you look at a similar stress strain, indentation force deflection curve for HR foam, you see it's a much more linear type and flatter in this range, and it's changing linear here rather than that flat slope. So what that means is that a person with a light weight as well as a heavy weight can both be sitting inside the foam rather than on top or bottoming out. And that all has to do with going back to that irregular cell structure I told you about for the HR type foams. The sag factor or support factor is taking the 65% IFD over the 25%. So the HR has a higher ratio, indicating better support. And the difference between the loading curves and the unloading curves is called hysteresis. Most people probably know what viscoelastic or memory foams are. Seems like it's all the new bedding and the toppers, the bed in the box type applications are all based upon viscoelastic foam, although it's been around for quite a long time. But these type of foams exhibit what's called a time delay response. So typically if you compress a conventional foam, it springs back essentially immediately, whereas viscoelastic foam, it takes several seconds for that foam to fully recover or respond. They typically have very, very low resiliency to them. And the properties of the viscoelastic foams are most often associated with the glass transition temperature of the polymer, and they target it to be around room temperature. And if you can think of the glass transition temperature kind of as a sort of a softening point for that polymer, at temperatures below the glass transition temperature, that the foam, the polymer can be very hard. Above the glass transition temperature, it becomes very soft. So by targeting it to have a glass transition temperature around room temperature, as you lay on it, the foam picks up your body heat and sort of softens and molds into the shape of your body. And these can be made by either a continuous or a molding process. Another difference between the three types of foams is the type of reactivity. This is a graph of how much the foam is rising as a function of time. So when you mix it, you dump it into your box or bucket, and you measure with some sonar or something like that rate of reactivity. HR foams react the fastest, then conventional. Viscoelastic foams tend to be extremely slow. And as we start to talk about the chemistry of the raw materials that go into it, you'll understand maybe why we see these differences in the reactivity curves. So if you look at a typical polyurethane foam formulation chemistry, not sure why this came out off-centered here, but it starts out with typically 100 parts of your polyol, your polymer polyol is always 100, and then all the other additives typically are based upon that 100 parts of the polyol. And lastly, then your other component is your isocyanate, and you can see depending upon the index and the type of foam you're making, that can only be a small fraction of the total amount of material that goes into a foam. So index is the ratio of the amount of isocyanate that's needed to react with all the hydroxyl groups that are present in your foam formulation. The hydroxyls from the polyol, from the water, from any other additives, cross-linkers. And 100 index is essentially an equal balance that is stoichiometric. It's 1-to-1 iso to polyol and other reactive materials. When 110 index means I have, say, 10% more isocyanate than is needed, that isocyanate will still react, and what it will do is do some additional maybe cross-linking or other reactions, and versus if you're say 95 index means you don't have enough isocyanate, so you may not get the full range of properties. But varying that index is a very common technique that people use to try to change the properties of the foam, mainly the hardness, by manipulating that index. Again, it's just the ratio of isocyanate to all the reactive groups. Now we're going to start talking about all the individual components that go into making the flexible foam, starting out with the polyols. And as you can see in one of the earlier slides, the main isocyanate that is used is TDI, whereas polyol, there's a lot of handles or different variables, so most of the functionality and changes that occur more on the polyol side than on the isocyanate side. So by definition, again, a polyol is just a substance with more than one hydroxyl group, and typically refers to materials with, say, a molecular weight that's greater than about 250. When it's small, low molecular weight, they're usually called cross-linkers or chain extenders or those type materials. There's two main classes of polyols used in flexible foams. The largest is the polyether polyols, and then there's also polyester polyols. There's a whole variety of other types of polyols out there, but almost none of them are really used in flexible foams. They're used a lot more in elastomers and coating type applications. So if you look at this polyol structure in here, essentially you have some type of starter molecule, and then you have a number of arms going off. So the variables on the polyol side can be the composition, what oxide was used along those arms, whether those N groups, those OH groups are primary or secondary, the functionality, in other words, how many arms are there, the molecular weight or the chain length can be varied, as well as the catalyst or the process that was used to manufacture that polyol. So as I said, there's a lot of variables here, much more so than on the isocyanate side. So just going through some of those things we talked about, the two main epoxides that are used are propylene oxide and ethylene oxide. And so you start out with the alcohol. If you use propylene oxide, you generate a secondary hydroxyl. If I use ethylene oxide, I generate a primary hydroxyl. And the difference between the two is the propylene oxide is what gives the polymer some flexibility, but it's going to make it react slower if it's at the end of the molecule. The ethylene oxide, if it's at the end, will make it react faster, but generally people also put it internal because it helps with compatibilization with the water that's in the molecule. This slide here shows the effect of that primary hydroxyl on reactivity. What we're plotting here is a viscosity build as a function of time. The faster that rate of reaction, the higher the faster that viscosity is going to build as a function of time. And what this is trying to show is that even small differences in the amount of primary, going from 75 to 80 to 85, really will affect that rate of reactivity. So it's something to be aware of there. So some of the other variables on the polyol synthesis side are the amount of oxide used. The more oxide that's added per starter, the longer that chain length. A conventional polyol is typically 3,000 to 4,000 molecular weight and usually based upon a glycerin starter. Molded and HR polyols are higher molecular weight and their functionality can be 3 or sometimes higher. Viscoelastic polyols are often the lowest molecular weight and sometimes have functionalities of less than 3. And some examples of what some of the typical starters are. If you wanted to make a diol, you might start out with something like propylene glycol. Glycerin is the most common triol starter. If you want to make higher functional materials, these are the most two common ones, sucrose and sorbitol, for flexible foams. For rigid foams, there's probably a whole laundry list of different type of starters to make other type of polyols. So you can add those oxides in almost any imaginable way you can think. Where you can start with the initiator and just put pure propylene oxide, or I can make a mix of propylene oxide and EO where the EO is on the end, whether it's internal or whether it's a block. So there's a lot of variability there to make sort of unique structures for different type applications. So the most common conventional is more like this mixed feed with a PO cap is the most common conventional. The most common like an HR usually puts ethylene oxide at the end, and having that ethylene oxide at the end, given that primary, is why in that reactivity curve it's the fastest to react. So as you say, typically you're putting in more PO if you want to make a more hydrophobic type material. You're putting the EO as a cap to make it more reactive. You're putting it internally for water compatibility. And then you're again also varying that molecular weight and functionality. Again, viscoelastic is the lowest molecular weight, and HR is the highest molecular weight. If you were making more of a rigid type, you're going to even have even lower molecular weights and much higher functionality. But so I mentioned that the other variable on the polyol side was the catalyst that was used to manufacture the material. The traditional catalyst was been KOH, been used for over 60 years, and one of the challenges or the difficulties with the KOH is it's a very slow. You can only make it by a batch, and you have to at the end refine or remove that KOH. A newer technology that has been around probably though for about at least 20-25 years now is called impact or double metal cyanide or some type of organometallic catalyst. So instead of large weight percent of the catalyst, you're using more like ppm levels. It results in an improved efficiency, environmentally friendly process. It can be made not just by batch but also by continuous, and you get increased productivity, reduced waste, but also more importantly, better side reaction, minimal side reactions versus the KOH that leads to higher quality polyols. So with the KOH, propylene oxide can isomerize to form allyl alcohol. Allyl alcohol contains a hydroxyl group, so it will react with more oxide to form a long chain monol, or also called unsaturation. Well, this monol, if you're trying to make a triol and you have this monol in there, that monol is a chain stopper, so it doesn't allow you to build molecular weight. So you don't get this side reaction with the impact of the double metal cyanide process. And this is illustrated here in this slide. So as the amount of monol that's formed by KOH increases as the hydroxyl number decreases, or this is the molecular weight increases. We'll talk about hydroxyl number here in a minute, but whereas you see in the impact of the double metal cyanide process, that amount of monol, the unsaturation, is constant regardless of the molecular weight you're trying to produce. And what that means, in effect, if most conventional polyols are about a 56 hydroxyl, so you can see 56 hydroxyl has an unsat of 0.03. If I convert that unsat to the amount of monol and the functionality, instead of making a 3 functional, I'm only now at a 2.7. And if I'm trying to make an HR polyol that's more like down here at 28, I'm twice that level, so I'm only at 2.5 functionality. So you're not, so when we typically talk about functionality, we're typically talking about the nominal functionality of the starter, but what's also important is what is the true functionality, and by using that new technology, the impact, you can make a much higher functionality, much more close to the theoretical type of functionality, regardless of the hydroxyl number. So at the last stages on the polyol manufacture, as I mentioned, if it's made by KOH, and a lot of products today still are, you have to remove that potassium down to a few ppm, and there's a lot of different refining techniques for removing that potassium, and many of them will leave behind different sort of cats and dog trace type impurities, which can often affect reactivity. So people sometimes say, well, I switch one 3,000 molecular weight polyol for another, and they're seeing a reactivity difference. It can also often be due to those impurities that are present in there. As I mentioned, the DMC polyols don't need to be refined. You just can leave the catalyst in them. Then the last step is to add antioxidants to help stabilize the polyol itself against oxidation, as well as when you go to make foam to prevent foam scorch or fires. So what are the important parameters to know or understand if you're working with polyols? They say, the The hydroxyl number, again, we'll talk a little bit about exactly what that is, but it's basically an indication of the hydroxyl content that you need to know for reacting with the isocyanate. Polyols are very hygroscopic, so they will definitely pick up moisture, so you have to keep them inerted for both picking up moisture as well as be aware of what that moisture content is for reacting with the isocyanate. And they are also susceptible to oxidation. Again, why you keep them needed under a nitrogen blanket, so that you're not forming peroxides or any color bodies or odor type materials that can affect reactivity or foam performance. Again, if you're dealing with a KOH polyol, you need to worry about is there any acidity or alkalinity remaining in the product, and also you need to know for the viscosity of what that polyol is for when you go, it will affect your mixing capability when you go into production. So as I said, hydroxyl number is an indication of the amount of N groups or hydroxyl groups present in the material. It's calculated using this formula here, and the 56 it's done by a titration method with KOH, and the equivalent weight of KOH is 56.1 times 1,000 is why you get this 56,100 times the functionality over the molecular weight. The relationship is just the equivalent weight is equal to the molecular weight over the functionality. Some examples are shown down here, and you can see if you take this molecular weight divided by the functionality, you get the equivalent weight for all of these. But if you know the hydroxyl number and know the theoretical functionality, you can calculate the equivalent weight and molecular weight. So as you see, if you had a 56.1 1,000 molecular weight, equivalent weight, and 3 functional, it's going to be a 3,000 molecular weight. If you had a 28.2, it's going to be 3 functional, it's going to be twice that equivalent weight. You can also have a 26.2 hydroxyl, but if the functionality is 2, it's the same equivalent weight, but the molecular weight is 2/3 of the 6,000. Again, short chains are, so the lower the hydroxyl. There's also some other type of polyols out there that are used. One class is the natural oil polyols. The 2 main natural oil polyols are castor oil. Castor oil already contains hydroxyl groups on it. The other is soy-based polyols. Soy polyol, the soy oils contain unsaturation, so the producers have to convert the double bond into an epoxide, then open the epoxide to form the hydroxyl groups. So that's a multi-step process. And some of the things to be aware with the soy polyols is, potential odor concern, and that odor can vary from sort of production process to production process. And also they tend to have a slightly acidic character to them, so that might affect reactivity. But people are using them in some formulations to be more environmentally friendly. But typically the amount that you can put into a typical formulation is fairly limited, maybe the order 10-20% at most. But often they can be used to impart more hydrophobic type properties to the foams. Another class of natural polyols is polyols that are made with the incorporation of carbon dioxide into the backbone. These are called polycarbonate polyols. You might hear them referred to as POCO2 polyols. So that double metal cyanide allows the carbon dioxide to react into the polymer chain. You're forming this carbonate linkage, and that carbonate linkage is very, very rigid, and as a result, polyols themselves tend to be very highly viscous, but that rigid structure gives them higher load-bearing properties than conventional type polyethers. These are only have been commercialized in the last few years. So the other main class of polyols that are used in flexible foam are the polyesters. Polyester is by definition, you react either an acid with an alcohol and remove water, or you can make it by some type of transesterification process. Again, to make a polyester, you need a difunctional acid and a polyfunctional alcohol. Again, there's a lot of variables here where you can have either aromatic or aliphatic, typically common ones are based upon something like ethylene glycol and terephthalic acid. Most of these polyesters are difunctional. They're very, very highly viscous. Can easily be 20,000 centipoise, whereas a typical conventional polyol is only a few hundred centipoise. They're mainly used in the flexible foam area for flame lamination type application. But one of the disadvantages of them is they're not as hydrolytically stable that ester linkage is susceptible to hydrolysis and get that reverse reaction occurring. Another family of polyols is called polymer polyols. And what polymer polyols are is a stable dispersion of a solid copolymer in a liquid polyol. And there's three main commercial type of polymer polyols based upon, the main one based upon styrene acrylonitrile. Another is called PhD for the German polyharnstoff dispersion. And the last is polyisocyanate polyaddition or polyamine or pipa type technology. They all have in common the component. You have a dispersing medium, which is your polyol. You have the polymer particle itself that was formed by that in situ polymerization, and you often need some type of stabilization, either added or kind of formed during the reaction. So when you form, let's say, the styrene acrylonitrile ones, you make a special stabilizer that typically contains unsaturation, so it looks like a monomer, and then it gets chemically reacted into the polymer network. And what that steric stabilization does prevents those particles from agglomerating and settling out. So unlike a filler that you'd put in and would almost immediately settle out, these things are fairly stable for years. So the styrene acryl is the most common type of polymer polyol out there. Again, it was developed, starting in the late 60s. You can get solids content up to about 50% solids, and you can get them both slab and molded type as the base polyol. The two main types out there are the high solids are typically higher styrene, and they're white, and they're typically very smooth type particles. And depending upon the process, whether it was a continuous or a semi-batch, you'll get a different particle size distribution that can affect your viscosity as well as some of the foam characteristics. Also, there's some low solid types still out there. They typically are higher acrylo, they're brown, and they're typically not quite as smooth, and that more like popcorn shape will give them different characteristics both in viscosity and in the foam. The second type of polymer polyol, as I mentioned, was the PhD. That comes from the reaction of an isocyanate with hydrazine. So essentially you're making a polyurea dispersion, and you get some in situ grafting. Typically they're fairly low solids, but the part of, since it's a polyurea, can involve, can benefit by giving improved fire retardant type properties. That last type, as I mentioned, the pipa is typically used in alkanolamine, like triethanolamine. So essentially you're forming a dispersion of a polyurethane in there. Again, these are typically lower solid content, and they're often made at the foam plant itself. So what is the benefit of using a polymer polyol? So the main benefit is kind of like if you have concrete and if you put a reinforcing filler, you're making reinforcing concrete. The same applies here. By putting those polymer particles, they get incorporated into the cell walls of the foam, make it stronger, give it higher load-bearing properties. So this is an electron micrograph of, you look at the cells here, the cell wall, and then you zoom in on it. You can see that the polymer particles are very well incorporated into the cell wall of the foam. The other main benefit is that they can provide some cell opening type properties to the foam, give a more open cell structure. So you'll see here that maybe not all the cells are open, and if you look closely, you might even see a ghost image in some of the cells there, just for Halloween. So what are the critical polymer polyol properties that you need to worry about? Again, as I say, is the base polyol, the styrene acrylo are typically in both conventional and HR. Some of the others are more on the HR type. Again, you need to know what the solids content was, because that will affect your load bearing. The viscosity, again, for processing, whether those particles were smooth or rough, and what that particle size distribution was, as well can affect your processing, as well as if you're doing a NovaFlex type process, can plug some of those screens or filters. Now switching to the second main component, the isocyanates. To say there's two main classes of isocyanate. An isocyanate, by definition, is a chemical with this structure here: the nitrogen double bond carbon, double bond oxygen. They're extremely reactive material. Again, a polyisocyanate has to have at least two. The aromatic, the two aromatic ones are either TDI or MDI. There's also aliphatic isocyanates. They're very, very slow reacting, very, very expensive. They're good for light-stable type coating applications, but they don't have the reactivity or the cost structure to be able to be used in flexible foams. So the two aromatic ones, as I said, are TDI and MDI. And they really vary quite differently in terms of their functionality, their molecular weight, the number of products. TDI exists as two isomers, the 2,6 and the 2,4. And you can see what the numbering system is here. Starts out with the methyl group on the aromatic ring, so you get the 2,4 and the 2,6 isomer. With MDI, you have three monomeric isomers and a lot of polymeric type isomers. If we talk about the synthesis, you'll understand why. But as a result, for TDI, there's only 3 commercially available products. For MDI, there's many, probably at least 50 MDI products out there. Functionality for TDI, it's always going to be 2, no matter which of the 3 products you have. For MDI, it's usually at least 2, but often it's higher than 2, and typically can go up to about 3.2. As a result of the differences in the molecular weight, it will affect the percent NCO. So you can see TDI has a higher percent NCO. That means if you're going to make a foam and you want to do the same index, MDI versus TDI, on a weight basis, you need to use more MDI in that foam formulation. And lastly, the MDI is typically more reactive than TDI is in foam formation. So TDI is made by starting out with toluene. You then do a dinitration, then a reduction of the nitro groups to the diamine, and then a phosgenation to produce the 2,6 and the 2,4 TDI isomers. So that ratio of the two really comes from that first dinitration step, and is directed by that methyl group in there. So during that synthesis, you always get an 80-20 ratio of the 2.4 to the 2.6. So this 80-20, or often referred to as TD80, is the most common TDI product out there. You can take that 80-20 and do a low temperature crystallization and get out almost pure solid 2.4 material, and then what you're left with is a 65-35 ratio. So that's how you get the three different products, TDI products: the TD80 directly from the process, the TD100, and the T65 through that low temperature crystallization. So almost everything, the main products in the U.S. are the TD80, T65 is used in some viscoelastic foams. It's more common in Europe, and the pure 2.4 is more used in some other coating or specialty or elastomer type application than in flexible foams. But the 2.4 is the more reactive than the 2.6 isomer. The primary use for TDI is in flexible foams. So that's by far the largest, really the only market segment for TDI, as opposed to when you'll see about MDI. So MDI starts out with benzene. You do a mononitration and then a reduction of the nitro to form the amine, which is aniline. You then do a formylation where you're doing a coupling reaction of these aromatic groups. And when you couple them together, you can couple them in a number of different ways to form both monomer and couple several rings together to form the polymer. So you then take this crude mixture of all these different monomer and polymeric amines, and then you do the phosgenation. So you end up with a mixture of monomer and polymeric MDIs, and you can separate out the monomers, and you usually have a mixture of polymeric along with monomer. And on the monomer side, you can separate out the pure 4.4, the 2.4 and the 2.2 usually come out as a mixture. So the monomer side, that pure 4.4 is, again, typically not used that much in flexible foam applications. It's more used in case and elastomer type applications. But what you're dealing with using in flexible foams is the polymeric MDIs, PMDIs. Again, they're typically much darker in color, so the foams themselves typically are even when they're first produced, are more brown in color. They're often mixtures of polymers and monomers. There's probably at least 50 different grades of MDI products out there that will they all have a very similar NCO content, but what they usually differ in is the functionality as well as that ratio of 2.4 to 2.2, or how the ratio of monomer to polymer. And again, they're typically much higher viscosity than TDI. And so the parameters you need to worry about for the isocyanates, for the MDIs, are viscosity, that NCO content, if there was any residual acidity from the production process, because you're doing that phosgenation. Again, you need to know about what was that monomer content, the ratio of the 2.2 to the 2.4, again, because they have different reactivities, and what was that functionality. Because unlike TDI, where you're getting most of that cross-linking through the polyol portion, with MDI, you're also getting additional cross-linking because they are higher functionality. MDI, as I mentioned, it's used in a wide variety of applications, not just in polyurethane foams. It's probably one of the smaller segment. The biggest segment for MDI is used in things like elastomeric type applications. Almost all rigid foam is MDI based, from insulation, from the roof, water heaters, refrigerators, So almost all rigid foam is MDI as the isocyanate. Again, because it's higher functional, gives you that more cross-linking. But also MDI is a great binder. It binds a lot of wood products together to make particle board, flake board, and materials like that. Now, if we look at the isocyanate products by the end application, conventional foams are essentially exclusively all TDI based. HR foams, there is some that are based upon MDI. The majority is based upon TDI. Viscoelastic is a little bit the reverse. Most of the viscoelastic foams are MDI based rather than TDI based, but there is some actual people who make foams using a blend of TDI and MDI for viscoelastic technology. Molded foams, again, uses both isocyanates, majority being TDI. Before I leave the subject of isocyanate, I just want to spend a few minutes talking about the safe handling of them. They are extremely reactive material, so the proper precautions for the safe use and handling of them really need to be followed. So they have been used very safely in large-scale industries for decades. They have a very, very low vapor pressure, but you can get overexposed to them if you're not working properly or safely. And the two main health effects are either irritation or sensitization, and the target organs are typically your respiratory system, your skin, and if you're liquid, you have to worry about any splash protection. Various organizations like OSHA, this is the American Council on General Industrial Hygienists, they have sort of set safe occupational work exposure limits. What I want to point out here is these levels are in the part per billion level, so extremely low levels there. So the safe way to be working with them really is through your engineering controls of making sure that you're working in with the proper exhaust and the ventilation, that you have good industrial hygiene practices, and lastly that you do want to make sure you are wearing the proper protective safety equipment, the gloves and the goggles, as well as one of your occupational safety people can do some monitoring to determine if you would need to wear a respirator or not for the application. So the important things are to read and follow the directions on the safety data sheet, follow the recommendations from the organizations like OSHA, and often the suppliers will provide resources, as well as industry organizations like the PFA here provide recommendations, guidance, and assistance on the proper and safe use of handling the isocyanates. Last part, coming to all the different additives that are used in the formulating of the polyurethane foam. What I want to point out here is typically all these additives are added to the polyol side rather than to the isocyanate side. Typically, a lot of these might have groups that can react with the isocyanate, so a recommendation typically is all additives, if anything, get added to the polyol, not the isocyanate side. Mentioned that typically, to make the foam, you need to have a blowing agent, and typically that blowing agent comes from the reaction of water with the isocyanate to generate the carbon dioxide. But there's kind of a limit there that mentioned that reaction is exothermic, and it builds the urea structure or the hard segments. So if you want to make a really, really low density or a really, really soft foam, that's hard to do with just water. So you need to put in a different type of blowing agent, and the most common type is carbon dioxide gas, liquid carbon dioxide. And there's various processes for adding, how you add that, and they'll be talked about those mechanisms in the previous reaction, in the previous sections. So, but by adding that liquid carbon dioxide, minimizing the amount of water, allows you to make lower density foam without as high of an exotherm and allows you to make some softer grade foams. In some more in the developing countries, or in the lab, sometimes other, blowing agents like acetone or methylene chloride, are still practiced. One of the main components for being able to make the foams is the surfactants, and they provide an awful lot of control in that foaming process. We'll talk about that a little more in a minute, but there's a lot of, just like there's all the variety of polyols out there, there's a whole variety of silicone surfactants out there that are all tailored to the type of foam you're making. If you use the wrong type or too much of a surfactant, you can either not get that foam to stabilize or get collapsed. So, you need to choose the right surfactant and the right level of surfactant for the foam that you're making. If you look at the steps in a foam formation, you have your air interface with the polyol, the isocyanate being the heaviest, is on the bottom. And as you start to mix them, and then as they start to react, you're generating the gas bubbles, and then the gas bubbles coalesce, and that liquid is turning into a semi-solid and a solid polymer. The surfactant plays a role in all those steps, from lowering the surface tension, it helps emulsify all those components, it stabilizes those cells as it's being formed. So the surfactant is an extremely critical component in the foam process. Again, as I mentioned, there's a variety of different type out there. Basically, surfactant is a polysiloxane backbone with a polyether side chains. And you can see you can vary the length of that polysiloxane backbone, whether it's long or short, as well as the number and the length of those side chains. Again, just point out that there's many different types of silicone surfactants out there, and make sure you're using the right type for the type of foam you're trying to produce. And the surfactant suppliers can all provide the recommendations. To mention also, the level of surfactant is also very critical, that you need to have the right amount of surfactant. If you have too little, you get splits or even collapse. If you have too much surfactant, it will cause the foam to be tight and really shrink or prune up like is shown here. So the other component are the polyurethane catalysts, and there's specific catalysts that will catalyze the gel reaction and others that catalyze the blow reaction. And again, foam formation really requires a balance of those two reactions. So choosing that proper ratio of the catalysis is important. Typically, the gel catalysts are tins and a few specific amines. Most of the amines are more of a blow catalyst. So the gel catalysts are the tin catalysts, and materials like TITA or A33. A lot of other amines like A1 is more of a blow catalyst. And a typical foam formulation, you're going to use a mix of blow catalyst, a mix of gel catalyst, both A33 as well as the tin. So you're often using a mix depending upon the type of foam you're trying to produce. So this is just some showing chemical structures of the catalyst. As you said, the tin catalyst is really to help with the gel reaction. Again, just like the surfactant, too lower level, you're going to get the tin splits due to insufficient cross-linking. If you use too much, it's going to make the foam too tight, and extreme cases, it will shrink or prune up. The most common tin catalyst that's used is stannous octaweight T9. It is hydrolytically unstable, so that's why it typically gets last right at the very end, right before the isocyanate gets added. There are some formulations that use T12, dibutyl tin dilaurate, but they're still used in some systems, but think it's been pretty much banned or outlawed for use in Europe. But that is, a hydrolytically more stable catalyst. Another class of catalyst is called the non-fugitive or non-emissive. As concerns over the VOCs or volatile organic compounds, inflexible foams is becoming more of an issue or importance or focus. To avoid using the standard amines, what the catalyst companies have developed is these non-fugitive or non-emissive catalysts. There's two main ways there. One is to basically make a larger molecule, a higher molecular weight, so it's not as volatile. And the second is you can incorporate a functional group. There's some examples shown in here that can then react and incorporate into the polymer network itself. Let's say as a result of the fact that, they're either higher molecular weight or get incorporated, you typically have to adjust the foam formulation and use higher levels of these type catalysts versus the standard catalyst. Another class of amine catalysts are delayed action catalysts. They're often used in molded foams to allow that all the liquid ingredients to completely fill the mold before starting the reaction. And the catalyst suppliers take an amine, react it with an acid, and it forms an amine salt. So when you're using it, what you're doing is you're really adding an amine salt, and as that polymerization reaction kicks in, the heat from the exotherm makes it do the reverse, generates that amine catalyst to catalyze the polyurethane reactions. So some of the other polyurethane foam components are things like chain extenders, cross-linkers, and other modifiers. So these are typically low molecular weight. They can be hydroxy or amine terminated, and they typically react with the isocyanate to do some type of additional cross-linking reaction depending upon what you're trying to achieve there. If you want to, maybe some of them you could be using to get better stability, or you can, some of them are for making, having better density gradients from top to bottom of the foam. Some, will give improved cure. Some are put in there to make a firmer or a harder type foam. There's the whole variety of them out there. This is just a list of some of the common ones out there. And I think this really gets more into that art portion of what I talked about earlier, knowing which one to use for what you're trying to do. There's no really good handbook for teaching, which one to use. I think it comes through experience and training on your colleagues. The same thing for the various cell openers or cell modifiers. There's a whole range of those type products out there. And like all these components, so they're either in an aqueous or a glycol solution. They also contain hydroxyl groups. So you need to account for any of that water and the hydroxyl in your index calculations. Fillers are also sometimes used. If you're just using a filler like a calcium carbonate, you're typically putting something like that in to make it a higher density and lower the cost. Generally, fillers hurt foam properties. There are some fire retardant fillers like aluminum hydroxide or antimony or melamine that are put in specifically to achieve fire retardant properties. Many of these fillers will affect the reactivity, so if you're either adding them in or taking them out, you need to worry and may be able to adjust your catalysis for that effect. A little bit more about, besides those solid fire retardant fillers, there's also liquid fire retardant fillers. Again, a whole variety of different types out there, depending upon the type of foam test you want to try to pass. Let's say recent legislation change in some of the procedures. The use of fire retardants in foams has has significantly decreased. So just be again cautious, like fillers. If you're taking them out or putting them in a foam formulation, you probably will have to adjust the foam formulation to account for that acidity that was either there or would come in with the fire retardant. Another material that's often used nowadays in the viscoelastic foams are the gels or the polymer control agents. And what these are materials that can affect the heat capacity of the foam. For example, some of the phase change materials, might be things like a wax, a solid wax that's microencapsulated. And what it does is it absorbs the heat from the body and changes from that solid to the liquid. And then, after, sleeping on it, it will change back from the liquid to the solid to be ready to sort of start that cycle over again. But, so nowadays, you almost all visco foams you see with memory gel beads and phase change materials. They can be incorporated, through the whole foam or put on as a layer on top. There's a whole variety of different type of classes of these gel beads. Often flexible foams are pigmented sometimes for grade identification or for certain end-use applications. There can be either inorganic pigment, but more common is organic type dye material that has some functional group on it, like those reactive catalysts I mentioned, that it can then react with the isocyanate and be chemically incorporated into the foam. Another important ingredient is the antioxidant, as I mentioned earlier. Typically, during the polyol manufacturing process, the manufacturer adds the antioxidant depending upon the end-use application. So, but if you're going to be trying to use a non-slab foam into a slab application, you need to worry about making sure that the right antioxidant level is present by either measuring or adding additional antioxidants. I mentioned that foam reaction is extremely exothermic, and those buns can ignite or decompose. And people have set foam plants on fire from a result of that. So the most common antioxidants are sterically hindered phenols and aromatic diamines are the most common type in there. So they're used to everything from the polyol stabilization, prevent any odor bodies, prevent peroxides, as well as prevent scorch or the discoloration in the foam bun, or worse, that exotherm getting too hot and the foam catching on fire. So you really do need to make sure that you verify the antioxidant level, as well as calculate what that maximum exotherm is. There's a limit to the amount of water that can be put in to a foam formulation without that foam catching on fire. And lastly here is there's a lot of other additives like anti-static agents. You're trying to make some special type foams from, say, clothing or shoes. If you're trying to make foam that's used for, say, in warm, humid conditions, like outdoor furniture, you want to make maybe have antimicrobial or biocide. There's all variety of different types of additives in there, and again, like a lot of these things, these additives can affect reactivity. So you need to verify what that reactivity is on a small scale before going into production with it. So we discussed a whole variety of all the materials that go into the flexible foam. And there's many effects there. As I said, a lot of it is an art, but the science part, I hope I've told you enough to get you started in it. But I would say use the resources of the suppliers. All the suppliers can easily make specific recommendations on best how to use their products.